the objects around us using a scene understanding. First, let me define what semantic segmentation is. So here, given an image I and a collection of classes from L1 to Lk. So for example, these classes, we might think on them as, for example, being roles, frameworks, and so on. We have to produce a map between the input image space and the output classes space, as you can see here. And the question is how to produce this map, how to estimate this map. So related to this problem, we have also addressed in this session several issues and proposed several related approaches. So for example, I would like to highlight that we propose to improve the efficiency of this method by leaving out the computation of semantic segmentation in an offline state and then recovered by using and mapping. We have also proposed practical ways to deal with model adaptation online when we have a pre-trained model and we want to we propose also a tool to address this issue. And then we also saw a way to extend semantic segmentation model to a more challenging problem, which is change detection. But I'm going to be covering here today two of the most important ideas, which is how to practically train the convolutional networks for embedding devices, as for ground autonomous vehicles, and how to exploit virtual worlds in order to defeat the curse of the data scarcity. So first of all, I'm going to start by explaining how to use the convolutional network to train embedding systems. So in this work, we are using deep learning. Deep learning, we can define it as a way of given some input, training, and labels, we are able to have a correlation between these two by means of a model. So, but for that, the main problem is that nowadays we need high large volume of data. And that data is usually not available for driving scenes, for following semantic segmentation, and so on. So what can we do? The first thing we did here was to understand that was a problem. So we need to somehow find large set of annotated data. In order to cover that, we propose to mix data coming from different problems, so object detection and so on. But that brought new problems because that data is usually more noisy, it's quite different, and then when you put it together, you need to be able to deal with that. Basically, you end up with two incompatible domains, and during training, things get more complicated, as I will explain now. And then the second problem is that in order to have something working for embedded devices, we need to come up with compact networks, so the architecture has to be quite compact. And here, that makes things harder to train. Okay, so end-to-end training systems are not so well posed for training those embedded architectures. And we need to come up with some alternatives to come up with compact models that are still very efficient and accurate. So regarding the first problem, the first thing is to define the data set. And as I said, for that end, we brought the multi-domain role-destined semantic segmentation. So we put together more than 31,000 images from different domains. So we have the classical domains in semantic segmentation as Cambit, Kitty, urban label me, and CBCL that we have to re-annotate. But then, because these domains don't have enough instances of classes like pedestrian, cyclist, and so on, we try to incorporate a data set coming from object detection. So for that, we use ETH pedestrian detection dataset, the German traffic sign recognition dataset, Microsoft Coco, Kitty objects, and so on. The idea is that thanks to this, we are able to improve the statistics for classes as pedestrian or traffic sign from having a representation of 0.4% to having a more suitable representation of 13% and 3%. So we try to balance the classes a bit more. And this is quite useful for training semantic segmentation models. You can see here some example of how this dataset looks when they are normalized. In addition to this, we also try to address the problem of large-scale scene understanding. And to that end, we collected videos, random videos from YouTube all around the world, from different parts of the world, from Morocco, China, Japan, India, and Australia. The nice thing is that although we can only use these videos for qualitative evaluation, these are very challenging. So they are under very challenging condition of noise. They have different optics. Cameras are not properly set up. We have reflection and everything. What we would like to see is that the network is still able to generalize to those domains and perform as good as in the training. Okay, the second thing I would like to do is to define the metrics we are going to be using throughout this semantic segmentation work. So we are using the standard metrics of global accuracy and average per class accuracy. So the global accuracy is basically how many pixels have I successfully predicted, okay, without taking into account the class they belong to. That has the main problem of being biased towards the categories that are more predominant in the scenes, like for example roads or buildings. In order to compensate that, we pay more attention to the average per class, which is in the end an average of the accuracy of each of the different classes. So this is more fair in order to see how well is your method recognizing all the classes on average. So we will pay more attention to this second metric. Then we also need to define a suitable model for semantic segmentation, because we need to remember that we are focusing on ground autonomous vehicle, and that means embedded devices. So those are very memory constrained. So usually when we use chips for implementing this method, so they have less than 10 megabytes of memory. So we need to get along with that memory, and therefore a proper architecture is required. So for that end, we propose this simple architecture based on 4 convolutional blocks and 4 deconvolutional blocks. It's becoming quite a standard right now, and it has been proposed using max pooling and unpooling method to recover the full size of the image. The good properties of this network is that it's very compact. It just has 1.4 million of parameters, which actually fits quite well in the network. It's very efficient, so it can run in real time, and therefore it's very suitable for embedded context. As a reference, we have also considered the fully convolutional network from John Long et al. At CVPR 2015. It's a very competitive baseline. It has been the state of the art until recently. They're a bit deeper, and it has many more parameters. So now we have more than 100 million of parameters, and the network now occupies more than 500 megabytes in RAM memory. So therefore, it's not very suitable for the embedded context we were talking about. But this is still a good reference, a good baseline to compare to, and to see that everything is going well. Okay, so when we perform our first experiments on the dataset we proposed before, the MDRS3, what we see is that when we combine the dense and the sparse domain, none of the training methods actually converge to a solution. So not ADAM or stochastic gradient descent. But when we only focus on the dense domain here, the method actually converges to proper solution in all cases. So the question here is why. So, and this was one of the first things that we have to address when combining multiple domains with different properties. The things here, so the simple explanation is that because we are using gradient descent methods, everything is oriented to have good gradients, and just selecting randomly data from both domains without taking more care, because they are having different numerical properties. So here you can see that, for instance, the dense domain is actually dense, so all the pixels are labeled, so they become quite informative and stable. So you will see buildings in the same position many times, road is pretty much in the same position every time, sidewalks and so on. But for the sparse domain, for the dataset coming from object detection, what we see is that the number of pixel labels are quite a few. So in the end, an image just a couple of pixels with information. That information is actually very, very good. Those images are quite informative, but the gradients of both domains are very different. So when we put those things together, sometimes at some point the network is going to diverge. So in the end, what we're trying to say is that we need to add some additional control to this problem in order to address this issue. So some additional constraints are required to cope with this specific issue. So for that, we have proposed 3 different alternatives. An alternative way of training is domain adaptation via data projection. The second alternative is called balanced gradient contributions. And the third alternative is just an ensemble of the different modalities. So I will explain this now in more detail. So for the first one, the sparse, the data adaptation by data projection, is just trying to bring the classical idea of having one domain, do some operation to transfer that domain to a second target domain. So the way we do this here is we consider the sparse domain, which is the conflictive one, and we take the masks given by the ground truth of the sparse domain and use those masks to crop the RGBs, so to get the objects we are interested in. Then select random images coming from the dense domain and use them as a background to inject the information coming from the sparse domain. So we can see this as a simple way of performing data augmentation that is going to end up in something quite informative and useful. The second approach is a bit more sophisticated, I would say, but it's also quite direct. So the idea here is that because we know that the problem is in the sparse domain, that is very informative but noisy. So here, for example, we can see a representation of the gradients. So usually the gradients coming from the dense domain are quite, the magnitude is sort of small, well bounded, while the magnitude of the sparse gradient is not well bounded. It has a large covariance and so on. So the idea here is, okay, to have two separated terms for optimization. So one using cross entropy over the dense domain, and then another one using cross entropy over the sparse domain. This second term is going to be seen as a regularization term for the first one. So this lambda is going to control the information that this gradient is going to provide to the final optimization. It's going to bound the contribution of the sparse domain. So still we are going to have the information of the sparse domain, but we will have it under control. In practice, this can be easily implemented if you know the equivalence between the lambda and the batch size. You can actually just implement this by having a fixed number of images from the dense domain and a fixed number of images from the sparse domain. You just need to find the balance that will usually is linked to this lambda. But this way is much simpler to optimize, so you don't need to care about the proportion of images. Okay, the last proposal is to do an ensemble of modalities. So this is basically training a network on the dense domain and a second network on the sparse domain. You fix and you freeze those networks, and then you combine them, adding some residual modules here. And this is actually the approach producing the best results. But the main problem is that now we have double number of parameters, so we increase the number of parameters to almost 260 million of parameters, taking a gigabyte of memory in RAM, which is clearly not suitable for embedded context. Okay, if we have a look to the numbers, what we see here now when comparing the different training methods is that usually the ensemble for both networks, the FCN up and the TNet down, is that always the ensemble is performing the best. So in terms of per class accuracy, we here get 46% versus 42 and 45, and the same for the FCN, so 61 versus 57 and 53, and the same goes for the global. So now we are able to converge using all the data, but the problem is that, as you can observe here, the TNet, the small compact network that we proposed, is not really matching the precision of the FCN, of the state of the art. So state of the art gets 61 and we get 46. This happens in all the modalities of training, so FCN always gets better. And we were wondering why, because the FCN is too big for embedded devices, so we would like something smaller, but TNet is not accurate enough, so we would like to come up with a balance. So how can we reach a compromise? So the first thing you might think is that the problem is coming from the number of parameters of the network. So in the sense that the tiny net doesn't have enough capacity, but that's not the main issue. So here we observe that when adding much more data, the network was still able to keep learning properly until matching the performance of the FCN. So what is happening here is a bit different. So it has more to do with the way we optimize and we perform the training and the parametric space. So we can give an intuition saying that larger parametric space in the end present a simple structure for optimizing. So when we want to achieve some specific solution, if we have a smaller parametric space, then in order to achieve that model, that representation, the space has to be twisted. And in a twisted space, just using unconstrained optimization method is quite harder to reach a proper solution, so a good solution. And you get stuck in worse local minimum. So in this case, as long as you don't overfit, the larger your space is, the simpler it's going to be to optimize it, as long as your gradient is flowing well and you are not overfitting. Having this idea in mind, what we proposed was to start training a large network, so an ensemble of FCNs, and then use the output of that network to train our target net. So the idea here is that usually you don't have enough information to train the target net end-to-end with simple methods, because there is a lot of noise, then the parametric space is twisted. But if we first use the source net and we take the output of the source net, first we have more information because we can add more images that are unlabeled, and the source net is going to label them for you. And also we can take the probability distribution over the different classes, so the softmax outputs, and we can use the whole probability distribution for each of the pixels to train the network. So we have more information to train the network. Instead of just using labels, we can move to use entire probability distribution. And this is usually quite a fast way of training the network. So here you can see the target net during testing. So during training, we first take the input raw data, put it through the source net, which in this case is going to be an ensemble of FCNs, get the predictions, for example, the probability distribution, as I said, and use that to train the target network that we are interested in using cross entropy. During testing, it's just as simple as taking the input data and feed it to the target network. So it becomes completely independent from the other network. Okay, in order to test this concept, we propose 3 different flavors of this idea that we call transferring knowledge. The first idea is just using the labels, as I said. So basically, you have more data now that you can add to your domain, and then you just use that data to try to sample your source network accordingly, so the parametric space of the source network through the whole new data set that you can label for free. And you use the resulting label to train the target net. The second approach is a bit more sophisticated and uses more information, and just consisted on using the softmax probability, so the whole distribution, to use cross entropy to train that. So this is using just soft assignments to exploit the information of the soft assignments to train the network. So for example, here we will find situations in which the network assigns a probability of 0.3 of a pixel to belong to a pedestrian, but also 0.4 of being a cyclic, for instance. And that's very useful information to learn and to perform training. And the last one is just a variation of the use of softmax probabilities, in which we also take into account the priors that we know, so the frequency of the classes in our data set, to come up with a more Bayesian way of formulating the problem. Okay, so the first idea, as I explained, starts by taking a new data set coming from Google Street View in this case, completely unlabeled, and now we use the source net to label it for free. And that output, those output labels are going to be used to train the target net end-to-end in a standard way. So this is a basic form of distilling that is called nowadays. The second method, as I explained, is also taking the data coming from Google Street View, but instead of taking the labels, now we take the probability distribution, because as I say, they are more informative. And finally, the last is a variation of the previous, as I explained, just taking into account the balance between the different classes using the prior information we can compute during training. Okay. We can see here that when we compare to the original results of our TNet, now we move for 39% of per class accuracy to 59% using our transfer knowledge method, using the softmax probabilities with the prior information. And this actually matches and even outperforms the performance of the FCN, which gets 50% of per class accuracy in our MN multi-domain dataset. So I would like to remind that all these experiments are being done in the multi-domain dataset. So we are using a very large collection of different datasets to testing, and that's why the situation is much more challenging than that, for instance, when applying semantic segmentation just over kitty, candid, or individual datasets. So, but I'm happy to say that we were able, by using these techniques, to actually get a compact model that performs quite well, even outperforming the behavior of the FCN. And we can see that here more clearly. This is a comparison of the different networks in terms of model size in millions of parameters and per class accuracy. Okay, so originally our target network was here, so it was quite small and compact, but it wasn't performing very well. When we compare it with FCN, different flavors of the FCN, for example, FCN train end-to-end, or with balanced gradient contribution on the ensemble, so clearly it was not much for them. But then, after transferring the knowledge from the ensemble of FCN to our tiny network, we were able to actually improve over FCN. It almost matches the performance of an ensemble of modalities with a network that is more than 1,000 times smaller in terms of parameters. So with a footprint of just 0.5% of the original memory footprint. Here at the right, you can see a comparison. I don't know if you're able to see this correctly, but it's a comparison of the different methods for a standard semantic segmentation image. So this is the RGB input image, and here we see the results of the FCN trained end-to-end, and these are the results of the ensemble. You can see, and if you can't, I will highlight it, that, for example, the pedestrians are now very well recognized. Here it gets a bit confused between pedestrian and cyclist. Also traffic sign, although the resolution is not quite good, that's well recognized. The original target network is not able to do that, so it's confusing the pedestrian, it's confusing the sidewalk, it's confusing the traffic signs and so on. But here, after we do the transfer knowledge procedure, we see that the TinyNet is now able to replicate the results of the ensemble of FCN quite accurately. And then the real challenge is to see how this method performs in completely unseen, as seen coming from the YouTube collection dataset. So here we have the input RGB. Those are the results produced by the standard TNet trained end-to-end. Okay. This is the output of the FCN. This is the ensemble of FCN, our source model, and this is our target model. So the TNet, but now after transferring the knowledge from SNet. And you can see how actually this network is able to match the performance of the SNet in completely unseen scene under very different illumination conditions, different camera conditions, and so on. Okay, I would like to conclude this part highlighting some of the most important points. So I think that the take-home message would be that we need to learn how to exploit partially annotated data, because nowadays we are living in this era of deep learning using supervised methods, so it would be very interesting to be able to deal with partially annotated data, although it's noisy. So when we have to deal with different situations that are not so standard, so when you don't have the proper data set and the proper architecture, when you have to add more constraints, then end-to-end training is not always the best approach. It's not going to be always producing the best model. So you need to add more constraints coming from your problem domain in order to improve that. And in this case, we discovered the transfer knowledge to create embedded models was a very good approach. So it's a very effective way of achieving a low memory footprint while keeping a high level of recognition. And then we have also shown that this method is actually able to generalize to new unseen domains by showing results in the qualitative dataset of the YouTube collection. Now, moving to the last part of this thesis, I'm gonna retake the problem of data scarcity, the scarcity in label. So before, in the previous work, I saw how we needed to combine different data sets to come up with enough information to train semantic segmentation model for urban scenes. The problem is that, well, in that way you have to deal with several issues, and still it's not enough data because we just managed to collect 30,000 images. And the first thing that came to our mind was, why don't we generate our own images? Why don't we exploit virtual worlds in order to produce all the annotation that we require and the scenes that we need to train our models for different tasks as semantic segmentation, change detection, and so on, so for scene understanding. So to that end, we propose Cynthia. Cynthia is a realistic simulation of driving environments. So we have different areas in Cynthia. We have rural scenes, highways, towns, cities, and so on. We also model different seasons and different lighting conditions, so down, night mode, and so on. We have many dynamic objects with high variability: pedestrians, cars, cyclists. And we have multiple sensors. We have 360 degree of view for RGB images, depth, and the semantic segmentation, of course, the labels. We are planning to incorporate lasers soon. And the most important thing is that we have automatic ground truth for instance segmentation, depth estimation, localization, change detection, and many other problems. Okay, this is how Cynthia looks like. So as you can see, it's not photorealistic, but it's pretty realistic. It's realistic enough to fulfill its job, which is to be able to train scene understanding method. And you can see the different areas we have. So this is more like a standard European town. The previous block was more like New York City. Here we are getting into the highway, and so on. Here you can see how we model different weather seasons. So you can see, for example, here winter, fall, summer, and spring. So the leaves on the trees are different, illumination is different, visual conditions are pretty different in general to be able to simulate those variations. We also see how we model dynamic illumination and weather changes. So here this is a rain in a scene, and this is a night scene, so where the illumination is quite challenging for semantic segmentation. You can see here a sample of our dynamic objects, so how the pedestrians are moving in a realistic way, and the cars, and so on. And the ground, which is one of the most important pieces. So here you can see the different distances, perfectly segmented in an automatic way, the depth estimation of the scene, given by the set buffer. But probably, if I have to highlight the principal advantage of Cynthia, is that we can get beyond human annotation. So we can generate ground truth for problems in which humans can usually not generate ground truth. We can generate ground truth for optical flow. We can generate ground truth for depth estimation. We can generate precise, very high quality ground truth for instance segmentation in a very cheap and cost-effective way. We can generate ground truth for very different problems of a scene understanding. Then, the second point that I would like to highlight is that we can also design the scene as we need it. So we can enhance visual variability. We can create frames in which we see tens of pedestrians, tens of different cars, different models. So each of the frames is going to be very highly informative. So when you use it during training, that frame is going to help you to move faster towards a proper solution. And we can focus on the corner cases. So for example, we can create the scenarios of car accidents, we can generate the scenarios of rain, weather, and so on. We can focus on the important things, which is quite opposite to the thing you have to do when you collect your own data set. So you have your robotic platform, you go there in a week, and what you get is what you have to annotate, and that's it. But here we can focus on the corner case. So In order to evaluate Cynthia and its relevance to semantic segmentation, we are going to use the previous architecture, so FCN and the TNet. We are going to compare different training approaches. So first, we will train on real domains and test on real domains. That will be a sort of baseline for us. Then we will start training on Cynthia and testing on real domains, training on Cynthia and performing a fine-tuning as a reference method for domain adaptation. And then we're going to use domain adaptation via the balanced gradient contribution technique that we proposed in the previous work to mix the synthetic domain and the real domain and see the result. So the evaluative metrics are going to be the same: global accuracy and per class accuracy, and the data sets are also as before, so Cambit, KT, human label mean, CBCL, and of course Cynthia. So this is the first result, just training on Cynthia, just using synthetic data and testing on the different real data sets. So things that I would like to highlight is that just using the synthetic data, we are becoming very good at classes as pedestrians or buildings or cars. Because as I explained before, Cynthia has been specifically designed to cover a lot of visual variability over pedestrians in all the different classes. So of course, for other classes, it's not so good, because these classes have more to do with textures. Textures are going to be different from the virtual world. So here we will need some sort of domain adaptation to get better. Okay, in this second experiment, I have covered the different domain adaptation methods over all the data sets. The conclusions are common for all of them, so are consistent through all the data sets. So I'm going to be focusing just on Cambit for both networks, the TNet and the FCN. The thing I would like to highlight is that if you observe the per class, so when training on Cambit and testing on Cambit, we get 50%, so real data versus real data. But just training on Cynthia already level up to 63% of per class accuracy. Okay, because we become very good at things like pedestrian, cyclist, and so on. But when using domain adaptation, we are actually able to scale some points, gain some points, and move forward to 66% of per class accuracy and 85% of global accuracy, which is a very good result. So a relative difference of more than 13 points in per class accuracy. While a standard domain adaptation method, as for example do fine-tuning, doesn't reach that far, so just improve 7 points. So our balanced gradient contribution method is actually able to provide a nice tool to perform domain adaptation, improving what fine-tuning method can do. So here, by fine-tuning, of course, I mean to train on Cynthia, fix the model, and then do some quick fine-tuning using the real data set, Cambit in this case. This is also true for the FCN network, so we have some baseline with the real data. And then, in this case, it's true that just Cynthia is not able to improve the results in terms of per class accuracy. But when using the proposed domain adaptation technique based on balanced gradient contribution, we're able to actually gain more than 7 points in per class and 3 points in global accuracy. So overall, I would like to say that our domain adaptation methods and using virtual data is actually good enough to produce good models with high accuracy for real scenarios or in autonomous driving systems. You can see here some qualitative results of the different methods on Cambit. So here is the normalized RGB image. Here you can see the original ground truth. This is the results for the estimation of training the network in a subset of Cambit and then testing on a different subset. And these are the results of testing on just Cynthia and then testing on Cambit. So you can see that it's not perfect, so the sidewalls are a bit messy, things that contain a lot of texture get a bit messy. But when you see cars and pedestrians or objects, so the network is very good at recognizing those without any adaptation. And then when you perform domain adaptation, mixing both domains, you obtain the best results. So you become good at objects and textures and so on. So the conclusion for this part would be that nowadays virtual worlds are a very practical tool to generate high quality images with annotations. We don't need them to be photorealistic, so this is a lesson we have learned. For this specific family of problems, we don't need photorealistic rendering, which is quite expensive. It takes a couple of days per frame. Here we can render more than 10,000 frames per hour with all the configuration of ground truth, for instance, segmentation, depth estimation, and so on. Therefore, virtual worlds are allowing us to produce high, accurate ground truth. We can actually define the virtual world as we need to enhance visual variability. We can focus on corner cases. So in the end, it actually brings a very nice tool to deal with scene understanding using machine learning. Then I would like to highlight that for me, the combination of virtual worlds and simple and effective domain adaptation techniques are the winner of this fight, because it allows us to actually have a very cost-effective alternative to standard methods. So we just need to produce virtual images cheaply, and then we annotate a couple of images from the real world, combine those, use domain adaptation, and end up with a nice model performing well in the real environment. So to conclude this thesis, I would like just to highlight some overall points. So we have addressed the problem of visual scene understanding for ground autonomous vehicles, dealing with the aspect of where, so the localization of the vehicle, and what, the objects around the scene, so semantic segmentation. We have built all this over a set of important tools, such as robust statistics, embedding theory, manifold optimization, compressed sensing, computer vision, machine learning, and so on. So I would like to give some specific conclusion for the problem of localization. So in which we propose more efficient and robust alternatives to classical pipelines, as for example Ransack. We are able to compute efficiently motion models over SC3, okay? And we have done this via compressed regression, fast optimization using manifold averaging, and also through the proposal of alternative models using robust PCA, fixed RAM manifold optimization, and so on. Then regarding the what, the semantic segmentation part, we have addressed practical problems in semantic segmentation, as for instance, how to speed up everything using semantic 3D maps with an hybrid offline-online approach, how to efficiently adapt models to new domains using unsupervised domain adaptation method. We have also covered how to train networks for embedded systems using knowledge transferring techniques. We also propose to use virtual worlds to palliate the problem of data scarcity and scarcity of annotations. We have shown also in the thesis how to extend standard semantic segmentation approaches to deal with the problem of semantic change detection, which is quite useful for performing a fast update of autonomous driving maps in a very efficient way, just focusing on the information that requires to be updated. As a future perspective, we have started to work on hybrid methods for localization, so that combine place recognition systems, so more topologically approaches based on deep learning to recognize places, and then go fine-grained using dense matching. And we believe that deep learning is going to become a very important tool also for localization. And regarding semantic segmentation, I think there is a huge need now to move really larger scale, at least for the problem of ground autonomous vehicles. So we have to start incorporating more information from noisy sources of videos, from YouTube, and so on. And we need somehow to come up with a way of evaluating our results on larger data sets. I think we also need to start thinking on introducing the virtual worlds as an element of the main loop of machine learning, so not to use it as an isolated piece in which data sets are generated, but has to be a an intrinsic part of the machine learning pipeline, just producing those images that are required for the machine learning method to keep learning properly. Also, active learning, we believe, is going to become very important when generating much more data. So the more data we have, the trickier it's going to get to actually select the proper images that are going to help you to train quickly. And for that, we are investigating active learning approaches to cover that issue. We believe that we also need to keep working on domain adaptation because better results are possible. We would like to keep decreasing the cost of annotation, so to get better results at the cost of less annotation, and for that we require further research. Now I would like just to finish by highlighting some of the contribution and achievements we have done during the thesis. So we got a patent with Toshiba for the transferring learning for the technique for creating embedding models using transfer learning. We published a book chapter in Springer about domain adaptation using virtual worlds. We have submitted several contributions to top journals as science, for example, the Transaction on Intelligent Vehicles or IGCV and so on. We have accepted papers in top conference, for example, CVPR, RSS, BMC, IV, and so on. We have the pleasure to get an honorable mention this year. We were finalists for the Best Paper Award, Best System Paper Award at Robotic Science and System Conference, RSS, for our paper on change detection using deep learning. And we have participated doing diffusion of science dissemination throughout several venues like CVPR or in Barcelona or even here at CMC. We got some recognition from the media from our latest research on virtual worlds and using synthetic data for training deep learning methods. I'm happy to say that a large part of my research has been used by several companies in the industry, as for example in Toshiba, Volkswagen, or nowadays Synthia, that is used in Intel, Yandex, and many other companies. So finally, I would like to really thank to my advisor board, like Angel, Julio, Antonio, and Nani Ponsa for the help during this thesis, and also to my collaborators, because without them, this would have been just impossible. So thank you very much, and I would like to conclude the thesis here and just leave the turn to the committee to ask questions. So thank you.
Thank you very much for this presentation. So now we'll start asking the questions. First of all, I would like to congratulate you as your supervisor for the great work you did. I think that not many times you can see a thesis that is well written and have covered a lot of topics in deep learning. Also, when you read all the chapters and see all the topics that have been covered and the difficulty of them, I think that it's really overwhelming. So, congratulations for that.
Thank you.
Also, from a personal point of view, I like a lot the way you have explained the thesis of the part. And the main reason, and probably you know that, is that in our lab we have two main PIs, Paul and Jimmy. And whenever someone comes to the lab, he always says, okay, I'm the guy in charge of the where, and you might in charge of what's around the lab. And in your case, you have covered both of them. The thing is that during the last 2 years, I didn't have changed my mind a little bit about it, and I'm not very sure if splitting the problem in two is a good idea. In the same way that in the class we are trying to solve the representation and the mapping at the same time, and if you try to solve each of them individually, you don't get the best result. It's a kind of philosophical question. I was wondering, have you thought about trying to combine
in general, I would like to think that that's a good idea. That's probably one of the goals. But every time when I see people trying to combine both, things don't go as expected. So I will say that right now we don't really know how to combine those two things in a proper way. So when we try to add those constraints coming from geometry to semantics, or those constraints coming from the what to geometry, I think right now we apparently don't have the proper tools to do that. We can see some examples that are working sort of well. For example, the networks proposed by Fisherman et al. Trying to incorporate some specific layer dealing with geometry and transformations, or Handa et al. Also extended that work to 3D. But in the end, you still have to take very specific care of the geometry yourself, designing very specific layers that deal with the geometric side of everything. So for example, we have been trying also in the thesis to cover the problem of post-estimation using deep learning, and things didn't go as expected. So I think we still have to get our tools to more mature in order to do that fusion. But of course, that would be a great idea. For classical pipelines, we have seen that concept applied. For example, there are several works in semantic segmentation, I think by Georgia Tech, which they combine also geometry and putting both things together with classical MRFs and CRFs. Things are going better. But if we focus in the current pipeline, let's say using deep learning, it's still not clear how to come up with a solution, the proper solution, mixing both ingredients. So at least.
For example, if you want to do implementation in Unity and you have already the quality or maybe the quality of the test, you use that as a feature, as a input to your.
The thing is that when we have incorporated that information, and we have done it for several problems, for semantic segmentation, also change detection, it doesn't improve much. So when you analyze the literature, people trying to do that, people who have done that are, for example, David Eigen. The main question here is usually where to incorporate that information, or how to incorporate that information. Like, shall I incorporate it from the beginning? So will I combine all the channels and then let the information go through the network? Shall I incorporate it at some points? Because depth is somehow describing higher level feature than raw pixels, so maybe you don't have to add that at the beginning, you have to combine in a different way. So that is still an open question, and every time we have tried to incorporate depth information, for instance, to our pipeline, the results we got were not better than just using standard RGB. Even for problems where it might be more obvious that depth is important, as for instance change detection, in which in the end you have the two images aligned, and if you have the depth, you can clearly see that an object has changed. Even in that case, just using RGB was better. So we somehow need still to learn how to incorporate that information in the proper way. And I think that's going to be one of the important steps forwards in deep learning. So how to be able to use, to add constraints coming from geometry to improve our learning method.
So in that sense, you think that we're not going to have end-to-end systems, but we have to plug things in the middle of the network?
I think we will have to pay more attention to geometric details. So we would like to design layers in a specific way to cover the needs of geometry. I think it's not going to be so naive training like a black box anymore. So we are going to be more care more about where to add the information, how to add it. End-to-end is a good tool, but has some limitations. And now it's time to keep adding constraints that are coming from the specific domain, bring in geometry, a specific layer for geometry, and so on. And I think that's going to be happening in the present.
And also the other way around, because when I was doing your thesis, for example, you said that you were trying to obtain a dense estimate of the structure of the environment. And at some point, I think you say, when we are trying to estimate the top of a building, we get bad results because we don't have enough parallax or something like that. But if you have segmentation and you know that this is part of the building, you know the kind of structure you're planning to see, right?
Yeah, the semantic segmentation, this is something that we also have been working, but we didn't include it. Semantic segmentation can actually help to
the geometry. Great. So the rest of the questions I have are more about the intuition behind the algorithms. So maybe you can help me with something of this. So for example, in the first part of the presentation, you are talking about that splitting your matrix into two parts. One with the actual information and the other one is going to be a sparse matrix containing the noise somehow. It's a good thing. So why having a sparse matrix or the sparse constraint is a good thing? What's the intuition behind that?
Well, it's not about if it's a good thing. It's about that it's a more realistic thing. It's not because of the sparsity itself. So sparsity, so low round plus sparsity is just because that's one of the formulations we know how to work with.
Yep.
So we have tools that we. So the idea was that we didn't want to constrain our model to perform with the Gaussian noise. We wanted to go more realistic and to add different type of noises that are more realistic. So in this case, the main point was to be able to cope with unbounded magnitude of noise.
Okay.
So we were assuming that usually when we have a matching system, you can have matching errors, which are sort of uniformly distributed. In some cases, the matching error could be quite high, and in some other errors it could be low, but usually randomly, uniformly distributed. So the reason for using the sparsity here was because we were considering that that event was infrequent in the case of noise to the matching system, and because we wanted to be able to deal with an unbounded magnitude for outliers. So the sparsity was coming because we knew how to deal with that problem with the low rank plus sparsity constraint.
So the kind of noise you are trying to model here is just if you have a mismatch, or is also the noise itself in the measuring the image?
So both.
Both of them.
But we are making some assumptions that that's going to behave in a sort of sparse way.
Because in that sense, I was also a little bit curious, because if you think about the noise in general, it's going to affect all the components of the matrix, which means that it's not going to be sparse.
Yeah, the noise usually will not be completely sparse. It will be coming in small clusters, and then of course that's not the best situation for the model. But we expect the model. We expected the model to be still some to show some resilience to that property. Then later on, there were proposed new alternatives in which instead of trying to make the noise sparse, it was sparse by groups or group sparsity. So you can model cluster and so on. We also tried this, but the result by the difference between using the group sparsity node and the sparsity node was not very different. So it's true. So usually noise might come in clusters. But still, this simple assumption is able to cope with that in a fairly nice way.
And if you have more information about the distribution, is there a way to incorporate that information into the model?
Yeah, that's always the question we wonder. Like having more information seems to be useful, but in the end, do you find that you don't know exactly how to incorporate that information to make something useful with it to improve your result. Okay. So maybe with some description of how many groups of noise you have, we could convert the problem into a sort of subspace clustering problem. That may help. So some people have done this, but for real application, like usually that's not the case. You are not in this context, so I don't know.
All right. So also, if we go to the second part, we discuss about the VGC algorithm. Again, it's the same kind of question.
Yep.
The first thing is why the sparse representation is more accurate.
No, the sparse representation is not more accurate.
Okay.
So the sparse representation brings more informative, more informative. So usually it's basically because how they collected the databases. So when you take the sparse collection of data coming from object detection data sets,
I think it was 45. Yeah, that one. This one is fine, I think 45. Yeah.
Okay. So the sparse data coming from the object detection dataset is very informative. So you see pedestrian cars and so on in a very different point of views and so on. The problem is that it's the way they behave numerically. So they are usually very small cluster or just a few pixels and so on. So when you try to combine that data in a blind way with the dense domain, which is very stable, the buildings are always more or less in the same position, roads are in the same position. If you analyze the gradients of the mini batches of dense images, those are very stable, so the magnitude is quite well bounded and so on. While analyzing the gradients of the sparse domain, so because the spatial distribution, the class distribution, the number of pixels is very few, so the shape and the size of the gradients are quite, the covariance of the gradient is very high.
So the statistics are going to change.
Yeah, the statistics are quite different from the dense. So when you put those things together, one is acting as a source of noise to the other one. So the difference between noise and information is quite subtle. So here the plan is, okay, knowing this, having information of the domain, of the problem domain, so knowing that the one causing problem is the sparse domain, we can actually just sort of dump the contribution of that. So we can bound it, it's a sort of way of bounding the contribution of that gradient, so it matches the contribution of the dense, and in the end, if you perform a sort of gradient averaging of all of them, the final direction doesn't get crazy. It's something that is.
So this is what lambda is doing here.
Yeah, so it's what this lambda is doing here. So we separate the contribution of the sparse data set and the dense data set in the cost function, and the sparse contribution is going to be bounded by that.
Because I was trying to have an idea of an intuition again of what this lambda is going into in there, and if I try to compare this to classical techniques in classification,
it's a regularizer.
Yeah, but in that sense, you have an intuition, right? Because when you are in base techniques or maximum a posteriori, you always know that the weights or in your model have to be not go crazy, so you want to bound the norm of the weights, and then you can use these prior regularizers. I was wondering, what's the effect of this guy here?
The thing is that I always see this from the point of view of optimization. I'm more like an optimization guy.
Okay.
So in a numerical way, so for me, the important thing is the gradient. So the gradient needs to flow within some boundary. So it doesn't have to be too high, it doesn't have to be too low. I observed that the gradient for the dense domain were quite nice. So they were very well bounded, as expected, but the gradients were not so well bounded. So the intuitive thing for me to do was like, okay, we need to regularize this guy in order to make it compatible with our guy. From a more general point of view, with respect to the, let's say, a Bayesian view of this, I would say that because the sort of information present in the sparse domain, the variance of that information is very large, somehow you cannot base your entire model just on that information. It's good to contribute with a couple of images, but the core of your model has to be trained with something more stable.
Which is the dense?
Which is the dense. Because, so I would say that the dense one is easier. So if we see this from the curriculum learning point of view, the dense domain is pretty easy, so the point of view are quite similar. So as I said, buildings are always at the side, you have the side and so on. So that's a simpler task to learn, something you can learn fast. And then the sparse images are much more challenging. So you have a lot of variation in poses, sizes, and so on.
So it can be because the dense domain, as it's more dense, you have more information impact, and everything is smoother?
You have more information, everything is smoother, and also, well, you have more stable information, meaning that you see something which is very coherent. So one image is going to be very coherent to the with the next image. So it's simpler to learn. So it's like, okay, sidewalks are going to be here, and they have this shape, and so on, and these textures. Buildings are usually here, and then the sparse domains is much more challenging. So it requires much more effort and probably some sort of preheating of the network. So we can say that the network is first focusing on learning the simple things, and then is compensating also.
Going to the details.
Yeah, exactly. That would be my view from the more general point of view.
Okay. Also in slide 48, I think, something that's not very clear to me because maybe I'm not that used to this architecture, is that you say, in order to improve the performance of the target net, you are going to use as an input the output of the previous one, right?
Yeah.
But later on in the deployment phase, you use directly the raw data
For
into
testing.
your net.
For testing.
Yes. No, that's the bit I don't get, because if the input during training,
For the labels, I mean, for the annotations. So the supervision we're gonna do of the target net in the training states is not gonna be our original ground truth, but the output of the net, of the source net.
okay,
So, but still the images are gonna be as usual.
all right. Okay, because I was looking at this
Yeah, sorry.
picture and yeah, it was a bit
It's
confusing in
for-
that sense. So I was wondering,
Yeah, for the
how can it work
It's for the
if the
supervision,
input is
yeah.
completely different?
Yeah.
Okay. Also on slide 52, this is out of curiosity as well. Yeah, so when you look at the graph on the left, you see the accuracy. I mean, even the best algorithms we have just make 63%, right?
Yeah.
You think this is going to be enough in order to have a
No, no.
autonomous vehicle?
No, of course not. This is just still a scientific challenge. The main problem, as I explained before, and I think this should be the take-home message from this, is that we don't have enough data yet, and we don't have enough conditions recorded in a supervised way with annotation to really train models to perform in a large scale situation. So right now, the largest data set we have for semantic segmentation is cityscapes, and cityscape is not so large. So at the end, it's about 5,000 images fully supervised label, like pixel by pixel, and then 5,000 images, 20,000 images that have been labeled like roughly of an area of Europe that is quite similar, so Germany, Switzerland, and so on. So we don't have data of India, for example. Then I don't think the problem right now is in the architectures. Of course, with better architecture, we will be able, and with better learning techniques, we will be able to learn more with less data, and that will be amazing. But I believe that the current architecture with more data will be able to do much better. So using the current, the convolutional ResNet, for example, with a large data set, will be something able to produce higher accuracy in the order of 80%.
So then you think it's a question of having more data and that's it, or?
One of the main things is going to be having more data. I think the second thing is going to be to be able to represent the problem in a better way. So for example, here we are dealing with 11 classes, but mainly for comparison with the state-of-the-art methods. But the most important classes and the most challenging are road and sidewalk. So focusing on getting a proper representation for these two things is going to be also a critical thing, in the sense that nowadays we're trying to, we're asking a machine to tell the difference for a specific pixel and say, this is a sidewalk. But that's something that probably you don't need. You just need the boundaries of the road. So that change in representation actually simplifies things quite a lot. And we have shown that also in our experiments. So representation is going to be one of the big players, especially because for standard autonomous vehicles, we are not going to need to deal with, for example, poles or sky. That's something that we might take out. And then data. So at least if we take into account the current architectures and current learning technology, having more data and with highly precise annotation is going to help a lot. The question is, I think, how are we going to be able to acquire that data and that labels, and if we can, for example, use virtual worlds to generate rich enough data to cover the full spectrum of variability in our work.
Okay. So my next question is about synthetic data. I was wondering if using this kind of data for this application, as you have presented here, seems to work quite well, right? You can improve your results a lot by incorporating this information into your system. My experience, however, with this kind of data, when I try to obtain better algorithms for depth estimation, optical flow, scene flow, and these kind of things, is not that good. For example, I've been working with Ankus Handa and these kind of data sets. And usually what happens is that even an algorithm that is not that good, for some reason, as the images are not that realistic, you can get a lot of information. There are still discrepancies in the pixels, so you can see depth. not with a simple eye, but the algorithm is able to see that. And I was wondering if you can give me an idea of why you think this happens.
Yeah.
Is it I'm doing something wrong, or is it because this application is different, and then for this application synthetic data works?
So that's the
fine?
main point. This is very application dependent. So we are not claiming that virtual data is here to solve all the problems. So with the current non-photorealistic conditions, we can use virtual data for problems as semantic segmentation, object detection, and so on. That has already been proved. Those things are focusing more on shapes and context and so on. For things like optical flow, it gets a bit more tricky, although Professor Thomas Brooks has explained that so in his seminar work of the FlowNet, he saw how it is possible to train an optical flow network using synthetic data if you do it using curriculum learning. So you start showing the network some specific motion, and then you move forward to harder motion. So using synthetic data, they were able to actually, right now, they're able to defeat the state of the art just on synthetic data. For other problems like depth estimation, that might get much more challenged. So right now, we are not computing depth. This is something coming from a set buffer. It might be very different from the aberrations of the algorithms you use for computing depth. So there, we somehow will need to learn a better way of rendering depth in virtual worlds in order to match the distribution of the real one. So that's something that we will need to explore. But in general, the main point I think is that this is very problem related. So for some problems that you might, for example, illumination estimation, for that you need like very photorealistic rendering. That will be not enough for that. And for some other problems, we will need to somehow match to create some statistics that actually are able to match what you expect in real life. So,
but why do you think for segmentation something not very complicated works?
Because well, if you observe the results, so it's going very well without any domain adaptation in those classes that are pretty much detected using shape, like pedestrian and so on, and then context. So something like if I see this piece, which is a road, or if I see a pedestrian, I know the pedestrian is going to be pretty much 90% of the time on top of a sidewalk. And if the pixel is at the left, I know that's going to be a sidewalk. So it's getting good at context, although we are not using any sort of refinement with CRFs. It's getting some contextual information, some information based on object. Then we need to compensate for the things that are more related to textures. So for example, the sidewalks and so on. Sidewalks are quite tricky because unless you have enough field of view and enough context, it's really hard to tell the difference between different networks. So you have to base your recognition in textures. And for those classes, it's not so good. That's why we need domain adaptation. So in the end, there is no magic here. So shapes are quite the same in the virtual and the real world. Textures are a bit different. You need to somehow compensate for that.
So I have more questions, but I suppose that over lunch we can discuss about them. So thanks a lot for your answers.
Thank you for your question.
And congratulations again for the thesis.
Thank you very much.
Right, thank you. Just you have a question? I also want to congratulate you with your thesis. I read it with pleasure. It's you did a lot of work. So I tell my students that with 6 chapters they can present their thesis, but you have 12 chapters. So there are 2 theses here. Well, congratulations. And okay, I want to focus on the second part of the thesis. So in chapter 8, you still use a CRF model for the semantic segmentation.
Yeah.
And maybe just a broad question. So nowadays, most people don't use CRFs anymore. There are some intents to put it on top of and to do back propagation through it, but it's not really giving that much gain. Could you explain me why deep learning, how does it learn the functionality which previously was done by conditional random field?
Well, I don't think they learn the same functionality. So conditional random field actually model things quite precisely in a Bayesian way. But in the end, In practical semantic segmentation, the sort of CRFs we were using were basically a smoothing box. So it's like so we were not really applying any fancy semantic segmentation method. Pretty much everyone was just trying to smooth things out. So after I get the classes coming from my classifiers, I want to add some sort of context and coherence here, and I do a step of smoothing. So if that's what we need, and apparently that's what we need, right now there are different ways in deep learning to do that. For example, the way you represent the problem is very important. It has been solved. So there's a nice paper, I don't remember by whom, but there's a comparison between the Oxford paper from Bernardino et al. About using CRFs as a recurrent neural networks on top of an FCN. There's a second group which actually compare, in terms of semantic segmentation results, completely end-to-end approach without using any CRF, and they got better results. What they did was simply modeling the boundaries of the objects. So there's a second network who has to learn the boundary of the objects, okay? And then they have to predict and correlate together with semantic segmentation. And by doing that, they achieve very sharp boundaries. So things were coming out very, very smoothly and so on. The second thing that usually makes you believe that you require a CRF is that you think that your network, for example, here sometimes some of your objects are split in 2 parts or 3 parts. And you say, hey, if I put a CRF on top of this, it will be quite clear that these things, when I take the probabilities of these parts together, it's going to be a car. From the point of view of deep learning, we have seen that that's just a problem of not having a large enough receptive field. Because usually, well, your architect, you have some image resolution of 1 megapixel or so, and then you have, say, 10 convolutional layers, 10 poolings, and so on. In the end, you reach a receptive field of maybe 100 pixels, and that's not enough. So, but now with the dilated convolutions, which are a way of dilating your kernel like exponentially with a sort of elevation term, it's very easy to implement, and you can achieve very large receptive field. So, using that, you actually solves pretty much the problem of having objects split in different pieces. So now you can see actually large cars, and you're going to be able to predict that as a car without splitting in pieces. So that sort of, these two things, the way you represent the problem, being edge aware and having larger representative field, from my opinion, that solves the need, that removes the need of using CRFs. So in the way we're using CRFs in semantic segmentation, which was pretty much a smoothing term. So we were not really, because at least in urbanized scenarios, you usually cannot take context from the upper left side and do something to bring information to the bottom right side. So here, CRFs are just a smoothing thing.
Okay.
And that can be done differently in level now.
Okay, thank you. So in chapter 9, which you didn't discuss here, I think, so you propose a one-to-many Reinhardt color transfer algorithm.
Maybe I can open the thesis and we can follow.
Yeah, maybe then equation 9.1. Page 90.
Page 90.
90.
Improvement, yeah.
So you have 2 domains, a source and a target, and you're finding the closest images in the source domain to your target image.
No, it's a bit different. No, so I have a source domain, which is the domain in which the models were trained. The target domain, there is no actually a target domain, so that domain is going to be changing through time. Then I have a reference domain. So I'm trying to put the target like to be more similar to the reference. So I have selected a reference. So the user has to select sort of reference domain, like for example, Kitty. I want my new images to be looking more like Kitty because I know that my model has been trained on top of Kitty, or Kitty looks just nice. So then we're going to try to make the new target domain to be more like the reference domain. It's not like the source domain in which the model were trained, but to the reference domain. There are three domains.
But okay, let's say the target domain differs from the reference domain in color distribution, because later you apply a color transfer.
Yeah.
So I would say that doing this distance in color histograms is a little bit strange. So did you think of doing this distance in the semantic segmentation space, or on something based which you get out of intensity, or
yeah, that would be great, but that's the chicken egg problem. So we cannot produce good semantic segmentation of the new domain because
not perfect, but also.
But
if you do ImageNet and you train the whole network only with gray images instead of color, you go down 3%. I know for semantic segmentation it's more, but you can still get some results based on intensity.
Yeah, I have to say that this work is like the pre-deep learning era in which models were not generalizing so well. So we were not able to actually get decent results, even decent results, with classifiers for the domain. So we need to use some sort of different statistics for that.
And another idea would be to look at the I was thinking to look at the closest image after transferring with Reinhard. So then you have to optimize that, of course. Would that be possible? Is that
that will be possible, but I think that will lead you to a drift. So if you
have too many parameters there, or you
no, I think it would be a bit drifty, in the sense that you are taking the new image and trying to put it on in relation to a dictionary of the reference image, assuming some basic constraints as sparsity and non-negativity and so on. Then you transfer that image, and then you want to re-optimize. Then I think in the end it will be like a loop in which you keep drifting away from the solution. I think that usually in those unsupervised cases you need to define clear basic general constraints, as for example the non-negativity constraint in this case. So one image has to be able to be represented by a few images of the reference domain. Try to work with that. So if you try to keep looping, in the end you end up drifting. We tried something like that and the results were not so good. Maybe that will require some additional constraint. But in my experience, you have to define basic constraints, so general but basic. So.
Okay. Then the other questions about chapter 10. I think also slide 46.
46? No, 146 you mean?
Slides, yeah. Yeah, so this network came out as the winner of the networks, and it's a little bit for me disappointing that there is very little layers which are shared between two networks. No, and do you think if you had more time that more layers can be shared between the networks?
We tried that and we didn't achieve to defeat this model. So we tried to share more layers and more layers and more layers, but in the end it was the winner conclusion. So we have put experiments for different configurations. We didn't put those on the thesis, but we try to have even full optimization of the two architectures at the same time and so on. But for some reason that we don't know yet, this is the best you can do right now with our data. So to train the two separate networks, fix them, then add the residual blocks, and that's it. So we also tried that and we didn't achieve the results.
And with transferring the knowledge to a target network, I think it's probably a couple of slides further. So the source network is, I was just thinking, was pre-trained on ImageNet and then fine-tuned on image segmentation.
I don't fully remember if the source network was pre-trained or...
Yeah, it says so in figure 10.3. but okay. Initialization with VGG16.
Okay, yeah.
So I was wondering, could you somehow also pre-train then on ImageNet the target net, or on the segmentation already the target net instead of starting from zero?
Yeah, it would be possible, of course. The thing is that when we were training the target network using this procedure, the network was converging really fast, like in a couple of hundred epochs, like it was already converged. I guess that, of course, initialization ImageNet might even speed things up a bit more, a couple of years or more, but the convergence of the network was already good. Yeah, I think it's a good.
And so in this let's say relation between the two networks, you only look at the final layer. So I remember from the work from Adriana, for example, that she also looked at intermediate layers. Does it make sense for you?
Yeah, we're trying. Yeah, exactly. We're trying also to. We're starting to do something similar to that. We're trying to add additional constraint and say, well, why not somehow having the activation from this layer, apply some sort of map, and compare it with activation of this other layer. The problem is that these architectures are pretty different. Not only in the size of parameters and so on, but if you see also in the standard definition. So let me show you. So, for example, this is a target network, okay? This target network is based on a set of convolution, but the mechanism we use for like doing the deconvolution outside is based on pooling and pooling. So there's a mechanism of transferring pooling indices from the pooling to the unpooling side. While the FCN is completely different. So there is no pooling here. Everything is based on deconvolutions. Okay, and then what is very important is those summation we have here. So the shortcuts transporting the gradient from one point to another to another point to another. So this difference in the type of architecture made very different to sort of propagate the activation from the source network to be useful to the target network. The idea was obviously to find some sort of transformation of those activations to match those, but we didn't really find a way to make something compatible with what Adriana proposed. So in the end, the obvious thing was to take the probability distribution coming from the softmax, use those as soft assignments, and that actually brings a lot of information and made things to converge quite fast. But yeah, we were trying to do that, and we are still trying to some sort of like the leitmotif here is like, okay, you have more information, why don't you use it? So we were trying to incorporate part of the information from the network, but still, I think maybe something like a hypercolumn might be useful. Like, hey, you have because that's a sort of abstraction from the architecture itself. Like you have your hypercolumn 1, hypercolumn 2, try to make them match. But at that point, hypercolumn didn't exist, so we were not aware of that. That would have been a nice idea. But yeah, maybe we could try using something like hypercolumns.
And in 46, if you the architecture, later you extend this work to change detection.
Yeah, change detection.
You can leave it at this slide, huh? But I didn't understand how you, because there are two images as an input. How did you change so you just changed the first layer?
Yeah, we just changed the first layer.
Okay.
We actually just take the pre-initialization from semantic segmentation, add some random noise to the parameter we replicate.
Okay.
And that's it.
Okay. Yeah, that was a small question.
Yeah.
Okay, so final question maybe. So if you could ask the graphics community to improve one part of their algorithms, could you What would be first on your wish list?
Procedural generation of cities. So I don't want to improve graphics. I think, at least for my problems, the quality of rendering is good enough for my problems. So I'm happy with my adaptation for textures. I would like to have a simple and effective way of rendering cities that the distribution of the objects are realistic, like in our world. So something which is, I would like to improve the fidelity of the simulation in a systematic way.
More of the statistics rather than
Yeah.
the object. Okay. Thank you.
Thank you. Okay, so let me ask you a few questions as well. Well, first of all, let me congratulate you and join the other members of the jury in congratulating you on the thesis. I think it contains a lot of interesting work and very clear as well. Now, in terms of questions, so about the first part, about the where, the matrix that you're trying to approximate, you mentioned, has at most rank 6, right? Now, can you give us an idea of what does it mean if it has rank less than 6, for instance? Are these degenerate cases, or?
I haven't observed degenerated cases in this configuration, but I guess if you only have translation, of course, then that would mean to have rank equal to 3 and so on. But the noise itself is cancellating that.
Of course.
So in the end, even if there is a degenerate case, we are not going to find it. We are going to go for something with some noise to come up with the 6th rank solution. So,
But for instance, you typically in street scenes you have a lot of planar motion, right? Does this constitute a degenerate case?
no, because actually this is a very nice question, because in the simulation, in the virtual world, we also generate a ground truth for visual allometry and so on. And at first we have just planar motion, so for example, go straight, no rotation. And that killed pretty much all the well-known methods for visual allometry. So with real zero rotation, all of them were trying to predict some sort of small amount of rotation. And in the end, I think my point here is like, even though in a scene, theoretically, you can have like degenerated cases with just like translation motion. In general, that's not true. So you always have some small vibration of your wheel. You are also spinning, rotating a little bit. So in general, in a car, it's very hard to really find like that degenerate case. In any case, our method will not be able to find a degenerate solution because the rank is fixed to 6. So, but we still hope that that's a good approximation.
This is also another question. So in the thesis you really have 2 methods. The first one, that's, well, more than 2, but the last 2 about the where part. The first one is trying to find something whose rank is less than 6 with a sort of a rank minimization kind of approach, and then the second one is with the fixed rank. Do you have an idea of which one is better?
So yeah, in terms of solutions, the fixed rank is better. So I guess that because you are fixing so finding the correct rank is very tricky. So when we have to deal at the same time, like with finding the proper rank, completing the matrix L, finding the layers in S, that's quite complex. So it's highly non-convex and so on. When you fix the rank, things get a bit, so that information is useful. The way of solving the problem gets a bit harder, but the final solution you get is usually better and more accurate than having variable rank. But I have to say, and probably Julio will agree, that the solution of that problem becomes a problem. So it's now non-convex again. But in our experience, the solutions you can find by fixing the rank is much better, and the conversion is also faster, even though the problem is non-convex.
So so based on this, so in the thesis, also the way you presented it here, you essentially have a product manifold. I think it's on slide 23 that you mentioned this. A product of 2 C4 manifold and an SPD manifold. Yep. In the thesis, you mentioned at some point that you really have a quotient manifold. Because there are some ambiguities if you have
there is a vertical space.
Yes. So, but you're not dealing with this quotient manifold at all, are you?
Because the way we create the metrics for the individual manifolds already get rid of that vertical space in practice. It's also true that for this one, let me reformulate this. We are not taking care of that vertical space. That's true. So sometimes what we observe is sometimes actually the method is a bit slow in the initialization. So some of the iterations are actually moving through the vertical space on the first iteration, but then I sort of stopped doing that and I start converting. So, but yeah, we observe, because we also try with an alternative representation that doesn't have this vertical space. It's more like a trilinear factorization, so in which instead of having an SPD, you have FR. For that, you don't have that vertical space. And actually, we're able to convert in less iterations. So yeah, we saw that sometimes the method gives the first iteration to a vertical space. But taking care of that constraints was a bit tricky and more complicated. You need Lyapunov equation and so on. The thing we were trying to achieve was like high efficiency, decimally speaking. Just introducing that was a bit counterproductive. So even though sometimes we are moving through the vertical space, it's just like it's not really affecting too much the performance. But yeah.
Okay. Yeah. And so I have a more general question about this part, which is, in a sense, you're assuming that the scene is static, or you're trying to localize yourself with respect to the static scene. Now, in driving situations, you have a lot of dynamic objects as well, right? How do you see a way to incorporate them somehow? Or?
Well, we're assuming that the scene is locally static. So we're moving from frame A to frame B. The way of dealing with a more dynamic scene, I think, will be like reformulating the problem as more like a subspace factorization problem. You have different motion and so on. But I have also been studying these problems, and I was not able to achieve good results in practical scenarios, like for simulation and so on. When you have very well-defined motion, like fixed camera and just a couple of objects moving, it was working. But for moving camera, moving objects, it was very hard to find the correct number of subspaces and to really find the different distributions. Was really challenging. So that's a nice thing. I think it requires like more research. Also, will require to use different norm, like moving to group norms and so on. I have seen works related to that, but all of them are dealing with the problem in a very constrained way. So camera is fixed, you just have some motion. We were trying to apply this in a more general environment with moving cameras, just assuming that locally the motion was sort of, the scene was sort of static. But yeah, I think that's a very interesting future line for work.
Okay. All right, let me move on to the second part about the what. So first, you give a couple of examples about the networks. I think on slide 41. And you mentioned that they did not converge. Learning did not converge.
Yeah.
Can you be a little bit more specific about what you mean here?
Yeah, that at some point the training explodes. So you have exploding gradient or vanishing gradients. The thing is that your network stopped moving, and the solution was terrifically wrong. So.
You've been using Adam
different. So we have been systematically using different. So we have quite a lot of experience training this sort of network. So when we train the domain separately, dense or sparse, it converges perfectly with any of the optimizer, ADAM, AdaGrad, standard CD, all of them. No matter of the initial parameterization, when you put the data together, use the same things with the same parameterization, it doesn't converge. You change the parameterization, it doesn't converge. So at some point, you receive a mini batch, a killing mini batch that screws your gradient up, and then you don't recover from it.
Okay, and so when you have your new loss that you separate in two parts, then you have this parameter lambda that's in between, right? And so depending on how you set lambda, you might end up having problems in terms of convergence as well, right?
Exactly.
Do you have an easy way of doing that?
Well, through a lot of experimentation, we found out that, It was quite simple because we were observing the gradients all the time. So we were finding out how the good gradients look like the magnitude of the gradients and so on. So then we just have to find the lambda that actually like shrink the gradient to the correct size. So that was our way of finding.
But it's a fixed lambda, or lambda can vary throughout optimization?
In our experiments, we fix the lambda.
Okay.
So it's actually 0.1. But that's just because we found it experimentally, like comparing the size of the gradients.
Yeah, but as long as it works on all the experiments, that's fine. Right? And so now that the distillation, can you give me an intuition of why, when you're trying to match the full distribution as opposed to labels, it works better?
Yeah. So when you have labels, you just try to train with labels. You have in the end one value, and you have to propagate you have to readapt all your weights based on that single information. But now here, for each of the pixels, you have the full probability distribution. So you know that instead of having a spike that you have to match, not taking care of what sort of prediction or output you have to give for the other classes, so the network, when you train with the standard label, just care about saying, okay, for this class, 90% of accuracy, so I'm overconfident here. For the other, I don't really care, so 0, pretty much 0. Here is different. Here you say no. For a pedestrian, I have to say that I trust 80% that this is a pedestrian, but it could also be a cyclist, or 20%. So you have much more information than that learning from the source network. That additional information gets back propagated through the network, and of course you can adapt the weights accordingly better. So more information improves the training method and also speed it up. So the same happens when you try to solve a simple regression problem using deep learning. You just try to do regression of a simple variable, like for example steering of the wheel. Okay, the network converges quite slowly and sometimes don't reach the proper solution. If you add related variables, like the amount of gas you have to do, then the method converges faster because those things are related, that information is coherent, and you can use that additional information to propagate those things together.
What about the errors in the distribution? Because in the end, these distributions come from another network, right? So what if instead of pedestrian, it's actually very confident that it's something else?
You will learn to match the source distribution, but you are not going to get better than the source distribution.
Right. Okay. So this is why there's always a small gap between the source network and target network. Okay. On slide 54, you mentioned that one way forward would be to use more partially labeled data, or to better for partially labeled data. Have you also considered, instead of partially annotated data, have you considered kind of weak supervision? Now people have things like just with tags, essentially for each image, you say whether in the image there's a car, road, sky, pedestrian. That's information that's very cheap to acquire, but of course it's not as precise as annotation. What's your thought about this?
So I have been thinking about something similar to what DeepMind is doing now, to have these stack networks, okay? So like for multitask, and for me a task will be like, first I have this stack, this initial network, which is trained just on a supervised data, just to reconstruct the image. I have this second stack, which is trained on weakly annotated data. I have this stack, which is trained on like really densely annotated data and so on. And I would like to exploit all the information that we have available in the different ways, in the way DeepMind is doing with those stack networks for doing, I don't know how they call it, I think they call it stack network, no, continuous network or something like that. I would like to follow a similar approach. So you train one network for this, let's call it task, initial task, like it's going to be like to be able to reconstruct the image in a supervised way. You have your second problem, your second task, which is to predict like weak labels. So you have weak supervision, and you predict some classes like roads and sidewalks, like the general ones. But you also take the information coming from the previous network, so with horizontal connections. And then you repeat this process for all the information. I think that would be a nice way to keep building level of knowledge through a different task. Like, okay, I have this information for this task, let's try to make it useful for the next task, which is a bit more complicated. So it doesn't have to be a different task, but a refinement of the previous task. Something like that, it might be a way of...
And then in the end try to have a much smaller network that does
and then you try to find I think that would be
that makes sense. About the Cynthia, what about the Cynthia dataset? You presented results with the TNet.
Yep.
Was it the TNet that was trained from scratch, or actually also you trained the ensemble? And
in this case, it was trained from scratch. The difference here is that we have much more information. So now with Cynthia, the amount of images is much larger, and the amount of we try to get a balance between different classes. So the conditions are pretty different from before. So when we collect the different data sets, different modalities, and so on.
So do you think you could still gain something?
I think I could still reproduce the results and get as good as the ensemble of FCM.
Because in the end, the ensemble, if you train the ensemble on Cynthia, it also has access to more information, so hopefully you could do even better. And
yeah. The only thing is that I didn't really want to complicate this work, and I wanted to sort of isolate it from the other work. Because this just thing came sort of in parallel, so I wanted to...
Okay, I wasn't sure by reading the thesis, because the fact that it's called TNet, which T stands for target, I thought, okay, then there might have been a source.
It stands for target and tiny, but yeah.
I see. Okay. And just some more question about the framework itself. Now, you mentioned modeling, you're able to model corner kind of situations. Can you model things like dangerous situations, like traffic jams, accidents with bad cars, and things like this?
We can do it, but right now we have to do everything manually. So we have artists and modelers like working with this tool to steer in the situation. So the next step will be to find a way to do that procedurally in an automatic way. That's what we are trying to do for future work.
Okay, thank you. So I'm done with the questions. So is there anybody in the audience who would like to ask some questions? If not, then does the supervisor like to ask some questions and some comments?
Just a few comments. First of all, I congratulate for the hard work. As you all said, I always said there are two tests here for mine, and he's a hard worker and excellent work. And second, I wish you all the best for the near future that is starting soon. That's it.
I also joined with congratulations. He has done an excellent work. I also have some comments, but I think we can discuss at the lunchtime, because not to take too long.
Okay, in my case, I'm not going to insist in the quality of the work and the thesis. In this sense, only thank you for the Cynthia work, because for me, you know that this was one of my working lines, and it has been a big jump with Cynthia in this sense. But because I think there is family, and I'm not sure if all the family follows English, I will change to Spanish for a while. Y bueno, en este caso, pues yo lo que quería decir, para que lo sepa la familia sobre todo, que no solo es que Germán sea un investigador brillante, que eso ya lo ha demostrado, sino que también yo agradezco mucho los esfuerzos que ha hecho, pues, por ayudar a la gente que tenía alrededor, con las tesis, los estudiantes de undergraduate, bueno, en general a la gente que hay alrededor en el FUDC, ayudando, porque son muchas horas, digamos, invertidas en esto, y no tienen un premio, digamos, concreto, sino que es, bueno, pues es ayudar para que los demás mejoren también, ¿no? Entonces yo esto te lo agradezco mucho, porque cuestan muchas horas cualquier cosa que te pongas a hacer, y bueno, a la familia les insisto que es una gran persona, y además que bueno, que también es un investigador de nivel mundial, y esto se irá viendo cuando vaya a trabajar, pues, a sitios que tienen más presupuesto que el nuestro, y pueden hacer más cosas. Thank you.
Thank you. Okay, so at this point, I think we need to deliberate. I will ask the people to leave the room from both sides.
And one more, and we are for a join? No.
Ah,